Welcome everyone to this session of the AI for Net Zero webinar series. I'm Sarah Perez, postdoctoral research associate at Reactive University, and I will be your chair today, along with Professor Ahmed El Sheikh.
Hello, I'm Ahmed El Sheikh, and I will be co-chairing Sarah and hopefully supporting if there is any problem with networks.
Yeah, thank you, Ahmed, for that. So today it's a pleasure to host two early career researchers to engage in enthusiastic discussion around AI and sustainability. So please join us in welcoming them, and feel free to engage anytime in the discussion by writing your question or comments in the YouTube chat. So we will host a Q&A session at the end of each talk. So with further ado, let me introduce our first speaker today, Andrea Novoa, who is a postdoc on the UK AI for Net Zero grant in Aeronautics Department at Imperial College, working on scientific machine learning. Andrea has freshly passed PhD Viva from the University of Cambridge, so congratulations for that.
Thank you.
She has been awarded international prizes such as Amelia Earhart Fellowships and the Stanford University Fellowship. Andrea's research focused on real-time digital twins for sustainable aviation problems, from hydrogen propulsion system to aeroacoustics. Andrea, thank you for being with us today, and the floor is yours.
Thank you for the introduction, Sarah. Okay, so today I'm gonna present this work on real-time digital twins of hydrogen-fueled annular combustors, which I've done in collaboration with my PhD supervisor, Luca Magri, as well as Nicolas Noiret from ETH Zurich and James Dawson from NTNU in Norway. So the outline of my talk, first I'm gonna start with a brief discussion on what do we mean by a real-time digital twin, and then I will step on the definition of the components of a digital twin, which are a physical model, data from a physical system, and then also a bias estimator and a data simulation method that combines all of them. Finally, I will show you the application that we have been working on, which is this hydrogen-fueled annular combustor. The work of this presentation is mainly shown in these two publications. This one was published last year in Computational Methods for Applied Mechanical Engineering, and this second paper is the main focus of this talk, which is now in archive. Should be soon published in JFM. So what do we say it's a real-time digital twin? Because if you look in the internet, there are many definitions of what a digital twin is, and you can find everything from science fiction to any kind of movies, right? So in the science world, we define a digital twin using this latest report from National Academy, which defines a digital twin as a set of virtual information constructs that mimic the structure, context, and behavior of a system, and is dynamically updated with data from the physical twin. So this dynamically updated is what defines the real-time part of the digital twin. And in addition, we have this last sentence in the definition, which is there is a bi-directional interaction between the virtual and the physical system. And that is central to the digital twin. Now, so in the left-hand side, we have a physical system, which in our case is going to be an aero engine of a plane. And on the right-hand side, we have our computer with our models and our algorithms. So the digital twin is basically this interaction between these two subsystems and how we do that, because it's not as straightforward as it sounds. So what do we need to build this complex system? On the left-hand side, in the physical domain, we have data, which comes from sensors, for example, pressure taps, temperature measurements, velocity recordings, anything like this. The benefit of data is that's very accurate, but it's typically sparse in space and time, and also it's affected by background noise. And in the right-hand side, we have physical models, which here we have a larger variety. So we have models ranging from high fidelity to low fidelity models, and the difference is the difference is the computational cost and the accuracy of the problems. But in order to have a twin that dynamically updates itself, so it's adaptive in real time, we need to focus on the bottom of this pyramid. So we need to focus on the low fidelity and estimates of the physical dynamics at low computational cost. So the problem with low fidelity models is that because we make many assumptions and simplifications, we end up adding model error to our estimations. And this model error or bias is a problem because we cannot compare directly the physical model predictions with the data. So we need something in the middle to bridge the gap so that we can compare apples with apples, right? And in this case, we are using machine learning to perform bias correction of the low fidelity models. And now that we have a model that is corrected for the error so that we are in the same level as the data, we can combine these two things using bias-aware real-time data simulation. So this is the tool that allows us to put everything together. And now I'm gonna explain the specific application that we are looking at. So we are developing a real-time digital twin of a hydrogen-fueled annular combustor. And the physical system, so this is the annular combustor that is an experimental rig in NTNU in Norway. And this is a laboratory scale system, which is interesting specifically for propulsion systems. So this device, we have, this is a combustion chamber, and we have air fuel mix coming in here, and there's some flames that that are distributed azimuthally. So the fuel is hydrogen based, so it's the application is interest for sustainable aviation problems. So this would be a photo of the experimental rig, and this is a little video of the dynamics that you could see. So these are the flames that experience a thermoacoustic instability and end up disappearing. So this is a very complex dynamical system because it's multi-physics. There's a combination between acoustics, flame dynamics, and the aerodynamics and the turbulent environment of the combustion chamber. And another video of this experimental setup would be, is basically the same video, but from the top, which is the first one here. You can see the heat released spinning azimuthally, so rotating. So this is a rotation azimuthal thermoacoustic instability. So it's quite complex dynamics, and we want to develop a real-time digital twin that can predict the thermoacoustic oscillation. So the data that we have available in real time is not these tomographic cameras, but in fact is raw pressure from microphones. And in particular, we have 4 microphones at different locations. So at 0, 60, 120, and 240 degrees. And this is a little GIF of more or less the data that we have. So the white line is the raw data as it comes from the pressure from the microphones. And you can see it's sampled at very high frequency from, this is just 0.01 seconds. And the red dots indicate the data points that we are going to assimilate. So we are not assimilating every single data point that we get. And yeah, so this is the data that we have. So it's very noisy. It's sparse in space because we only have 4 locations, and it's also sparse in time because we don't want to overload our digital twin with too many data points. Second, we have the model. So this is a physics-based model that is quite developed in literature. So this model is qualitatively accurate, but quantitatively inaccurate. This is what it means to be a low-order model. So in particular, we have a wave equation here, in which in the right-hand side, we have the heat release rate, right? And the heat release, the law of the heat release, we are using these cubic expression. So the left-hand side is a linear function of the pressure, and the right-hand side is the cubic term, which measures the saturation of the thermoacoustic oscillations. And our objective here is to perform. Our objective here is to perform state estimation of the thermoacoustic state, but also parameter estimation of these 7 parameter groups. So we have alpha, which is the damping term. We have the frequency of oscillation. We have the heat source strength, and we have a few other parameters that we need to calibrate very accurately to different operating conditions. So this model is quite simple. It captures well the physics, and it gives us very rich behaviors. So the thermoacoustic instabilities can be or a spinning mode, as the one I showed in the experimental data, which would be this last one here. So you see how the pressure is rotating here, and in this yellow dot, which would be the microphone, we get this limit cycle behavior. On the top, we have another behavior of these thermoacoustic instabilities, which is a standing wave. So we have so it goes. The high pressure goes from up to down and then back. So then in the microphone, in this specific location, we have a very small limit cycle because there's no rotation through that microphone. And then we can also have mixed modes, which would be basically a combination of the top and the bottom options. And so we have the data, we have the model, and now we need a way of combining the two of them. And we are using a real-time bias-aware data simulation framework, which is the one we developed in this computer methods paper. In particular, we call this the regularized ensemble Kalman filter. So now I'm going to give like a little description on the method. But if you want to know more about the particular equations, just go to the paper or just drop me an email. So our objective is to replicate some state in nature. So in this case, it's just a gray line called the truth. So from left to right, we have time. And we have a model that we run an ensemble of simulations to try to predict this truth. And we forecast it in time until we have some observation D at some time tk. As I mentioned at the beginning, in order to combine the forecast with the observations, if the forecast is coming from a biased model, we need to correct this. So we need to estimate the bias that this prediction has project that into the space that can be compared to the data. And in this space is where we can do our assimilation. And so this analysis, where do we get this analysis from? So at each step that we have some data point, we perform an optimization step in which we minimize this cost functional J, which has 3 terms. The first term would be, we want to minimize, we want the analysis to be as close to our forecast, our best, first guess as possible. Second, we want our analysis to be also as close to the observations as possible. And third, we want our analysis to have a small bias. And this last term is the term that we have introduced, which is what makes this framework a regularized ensemble Kalman filter. And here we have the hyperparameter gamma, which is quite key to recovering small bias solutions. So if you put gamma to 0, then you will have just the usual data simulation cost function that gives you the ensemble Kalman filter. But if gamma is greater than 0, then we are penalizing solutions with high bias. Okay, so once we have this analysis state at time tk, we take this analysis step and we forecast it again with our numerical model until the next data point, project it to the bias state, and perform the analysis and propagate it, and so on and so forth. So the final thing that I haven't talked about is how do we estimate this bias, like how we project the forecast from the bias state to a state that we can compare with the observations. And we are proposing a machine learning method based in eco-state networks to infer this bias. We use eco-state networks, which are based on reservoir computers because they are very quick to train. It actually just consists of a simple linear regression problem. And you can prove that they are general autoregressive functions. So that's great to learn an unknown, which is this model bias. So now I'm gonna, I don't go into the details of the machine learning part because it's a bit of a quick presentation, but I will be happy to discuss that in any other time. So now I'm gonna show the results of state parameter and bias estimation. So just to recap, so we have a low order model, which we have unknown state and unknown parameters that we want to estimate. We have this eco-state network that I talked about that provides the bias of our model. And we have data from our physical counterpart. And the thing that glues everything together is this regularized ensemble Kalman filter. So our data informs the eco-state network and the low-order model about the state of the physical system. And the eco-state network informs the low-order model about the bias of its prediction. So let's look at, there's a lot of stuff in this slide, but okay. So here in the first panel, you see the 7 different parameters of the model, and the parameters are constant in time. But every time that we have data, so these red dots in the data point, there's a little step or a decrease on the covariance of our prediction. So it looks like the parameters are varying in time, but it's basically a step function that changes every time we have a data point. The second panel is the prediction from our model, and I have overlapped here the data points. So you can see that the data points are actually quite far away from the model prediction. So the model has already converged here, mostly in the state space, and you can see that the difference between the model estimate and the red dots is quite large. And this difference is the one that is being estimated with the machine learning model down here. So I hope that was okay. So we also can see the results of the state estimation in the statistical sense. So here we have the histograms of the acoustic pressure at the end of the simulation. And so this is the pressure at the microphone at theta equals to 0. So it's up here in the right-hand side. And the top panel shows us the model estimate in blue. Then we have the observations, the raw data in red. And then we have the presumed truth, which we define as a bandpassed filter version of the raw data. So this is our best estimate of what the truth is. Actually, we don't have direct access to the truth. And the second panel would be the model estimate plus the bias corrected term from the echo state network. So this is only one of the microphones. And here we have the results for the 4 microphones. So actually, you can see that the raw data is very noisy, and it's even biased because we would expect from a thermoacoustic system to have 0 mean, but the raw data has a mean that is greater than 0, which is given by these vertical lines. Okay, so then we also compare the solution with the classical ensemble Kalman filter. And in fact, in this particular case, the ensemble Kalman filter did a terrible job and was actually just predicting a fixed point because the data was too raw for the filter to find a good representation of the physics. Another thing we can look at is the generalization error. So this is the root mean square error of the ensemble with respect to the data and with respect to this presumed truth that I mentioned before. So again, the first line is the RMS between the model estimate and the data, and the second line is the model estimate plus the ESM prediction compared to the data. So from left to right, we have time. So in the left panel, we have the ensemble initialization. So you can see it's quite bad. We have a lot of concentration of ensemble members that are with RMS errors greater than 2. And the second panel would be a window of 0.01 seconds, I think, at the beginning of the assimilation. So you can see already that the ensemble is shifting towards smaller resolution, and already our echo state network is finding the gap between the model and the data. And we do this sequentially in time until we have quite a good representation of the system at the end of the simulation. And finally, this last panel shows the generalization error. So this means that when we stop assimilating data, is our digital twin still predicting the correct dynamics? And we can say that it is, because the RMS error is very close to 0. I think that that would conclude my presentation. And so what I have discussed today is a bit of a definition of what a real-time digital twin is, which is basically an adaptive model in which we have a connection between a physical system and some numerical simulations, and on the other way around. Second, I have described the components of the digital twin, which is some data from sensors that we can retrieve in real time. Second, a physical low-order model, which gives us quick estimates, qualitatively accurate estimates, but may not be quantitatively accurate and may include some modeling errors. So this is why we need the third point, which is a bias estimator, which is the ESN, which I haven't talked much about it. And then fourth, we need a tool that combines the information from these 3 sources. And in this case, it's the regularized ensemble Kalman filter. So yeah, I showed the results of this latest digital twin of the annular combustor that we designed, and we concluded that with this bias-aware framework, we can estimate in real time the acoustic state parameters as well as the modeling errors. Thank you for listening. I'm happy to answer any question now.
Yeah, thank you very much, Andrea. It was very interesting talk, very engaging. I only encourage the audience to post a question in the chat. We don't have any for the moment, so we'll start with questions from here. So yeah, my first question will be on the data sparsity effects on the assimilation, especially if you have like high frequency pressures evolution. Do you have any insight on how your data sparsity will affect your assimilation?
Mm-hmm. Yeah, that's a very important point, actually. We haven't performed any systematic analysis of the effect of the assimilation frequency, but the rule of thumb would be to have some estimate of the Shannon-Nyquist criterion. So you assimilate data about that key point of the Shannon-Nyquist criterion. The problem is when you start having chaotic dynamics, when things get a bit more intricate, and that's what we are working on now, actually. So okay. I will be happy to answer your question later on.
Yeah, sure. I mean, it would be more difficult to apply it on chaotic behavior for sure.
Yeah.
And keeping it on the data, so how do you handle the data heterogeneities between different sensors? Because I see that in your different sensor, spatial sensor, you have pressure evolution that range from different scales. So how do you, I think it was on slide 12, something like that. Yeah, here.
Yeah.
So how do you handle like this heterogeneity in the data?
Could you repeat the question? Sorry, I didn't fully.
Sure, no worries. From what I'm understanding, you have like 4 spatial sensors for the pressure evolving in time, and it seems like they both have very different scale, highly different scale. So for me, it looks like data heterogeneity, and I'm wondering how do you perform scaling before as on your input data, or do you have any tools to deal with these heterogeneities?
Mm-hmm. So in the data simulation framework, we have covariance matrix that scale the data, the different locations, and also compare this with the prediction with the model. So the model also predicts different scales, right? Because they are at different locations. One thing that we haven't done yet is use data from different locations. So from different sources. So in this case, we are only using pressure measurements. But what if we also used, I don't know, temperature tabs or something like this, which will have different units, different scales and everything. So that's that will be a very interesting thing to look at. But I think it would be simply adding this scaling factor before the analysis step.
Okay, thank you. Awesome. So in the meantime, we got questions from the audience. So we have a question from Alkes and Sam. So he says, thank you for the presentation, and asking for the generalization error. Did you test the performance of the model on a hidden set? And what was the loss function used to train the model?
So is this about the physical model or the eco-state network? Well, I will just answer both, I guess. So we tested this digital twin for different operating conditions of the combustor, so for different equivalence ratios, and it was generalizing quite well. So for training the eco-state network, we designed a way of estimating the model bias a priori, because we don't have information to the MLF model. Thank you. So we don't have access to the modeling error a priori, so we need to make a we need to make synthetic bias data somehow. And the way we did this was to create a set of, we drew an ensemble of initializations of the model and subtract this from the data, and that would create some synthetic model bias data in which we train the eco-state network. So this allows the network also to see different dynamics. So we didn't train it only in one data point. We created a very large, well, not super large, like around 100 different data sets. So this data augmentation was essential.
All right. Yeah, thank you. Thank you very much. We have another question. So maybe you need to clarify a bit more. So they're asking, is the error have zero means? And if you keep using the presumed correct model, isn't that propagating the bias?
As your errors have non-zero. Yes, so this is a very good point. Sorry, it took some time to understand the question. But so we use the biased model to forecast. So this analysis state is not the bias corrected one. So in addition to, so this is in the psi state. So it's still from our model. So we also have, as a subproduct of the analysis, we have a bias-corrected analysis, but we cannot use the bias-corrected analysis as an initial condition for our model because that will create a model drift. So we need to have the model in the biased state, and we need to have the closure of the model. So in a sense, is that with this eco-state network, we are learning the closure terms at the measuring locations. But we cannot just use those data points to forecast in time because that will create a drift in our numerical model. I hope that answers a bit the question.
Yeah, I think so.
Thank you.
Hamid, do you have any questions for Andrea?
Yeah, thank you, Andrea, for the interesting talk. I have a very small question about the value of gamma regularization, and do you think it should be constant along the time, or that's a big assumption?
So in this paper here, in the inferring unknown unknowns, we did a few systematic analysis on the value of gamma and also on the size of our eco-state network. And in general, we saw that the solutions change a lot with gamma, that for sure. But if the solution converges, it typically converges to the same parameters and the same state. So the gamma values are, if it's very close to zero, you are not penalizing your model, so nothing is gonna really change from your initialization. But if you go to gammas maybe around 3 or 4, then the jumps in your assimilation are too large. So the Kalman filter is allowing too much jumps, so you're gonna drift from any physical solution. So basically anything around 1 is the rule of thumb that I have seen by experience, but there's certainly a lot more to investigate in this gamma parameter. Possibly, like with inflation factors, there's adaptive schemes for ensemble filters of the inflation of the covariance. So possibly some adaptive scheme for gamma would be something very interesting to look at.
Thank you.
Yeah,
thank
you. For sure, I do agree with this point. So yeah, I think we can thank Andrea again for his talk, and we will move to the second speaker for today.
Thank you very much for inviting me.
Yeah, it's been a pleasure. So I'm pleased to introduce one of my colleagues, Marcos Cirne as a second speaker today. So Marcos is a postdoctoral research associate in machine learning at Edward University. He has a background in computer science and worked as an AI researcher at the Artificial Intelligence Laboratory, Recode AI, at the University of Campinas in Brazil. And his research interests are on machine learning, image processing, computer vision, and computer graphics. And today he will present a data-driven approach for reactive dissolution in porous media using deep learning. So, Marcos, please, the floor is yours.
Okay, thank you, Sarah, for the introduction. Hello, everyone who's watching us. Let's introduce this talk about deep learning approach for reactive dissolution in porous media, a data-driven approach. And this project is sponsored by EPSRC and co-authored with Dr. Hannah Menke and the professors Florian, Professor Julian, Professor Ahmed El-Sheikh, all of them from Harvard University. We all know that we're currently facing an imminent risk of global warming within the next decades, within the next 2-3 decades maybe, especially due to the emission of greenhouse gases. If we do not reduce these emissions as soon as possible, we're more likely to face a series of catastrophic events in our environment. So one possible solution to mitigate this global warming and achieve those net zero targets, especially by 2050, is find a way to store those gases back into the subsurface. So that is the essence of what we call carbon capture and storage, or CCS. And one possible way to accomplish this carbon capture and storage is by means of a method called reactive dissolution. So what does it look like? So reactive dissolution is a process that involves interaction between a fluid and the solid matrix that is contained within a porous medium, which in turn, when this interaction occurs, there's a lot of dissolution of minerals, which in turn they change the internal structure of the subsurface. So this leads basically to a series of trapping, mostly mineral and chemical trapping, which store the CO2 in the subsurface. And also, when we talk about this carbon capture storage using reactive dissolution, this process is important for several reasons. So we can list some of them. First is for stability and security of CO2 storage. And also, when the dissolution occurs, we also can notice an enhancement of storage of capacity and CO2 injection rates due to the changes in both porosity and permeability. And because we are changing these structures of the subsurface, we need to be aware with long-term behavioral consequences of that, because this changes, these chemical changes to the subsurface, if we don't do those correctly, the trapped CO2 can go back into atmosphere. So we also do this reactive dissolution to predict, understand how the CO2 plumes migrate within the storage formation. But this problem is typically hard to model because we have several kinds of trapping. So we have this graphic showing the different possibilities of trapping. And each of these trapping mechanisms, they take different amounts of time. So it can take to dozens of years up to tens of thousands of years to happen. And not only this, but these trappings, they happen at the scales of pores, which are in the order of magnitude of 10 to the -6 meters. And when we try to model these phenomena and all of the interaction between the fluid and the porous medium, we usually model this in orders of kilometers. So there's a huge gap between the pore scale and the scale we use to model those interactions. So, and this discrepancy leads to several uncertainties in these estimations of all of those iterations. So usually we make use of numerical solvers for simulating these processes in the case of reactive dissolution. But typically these processes are very expensive, which can take like a couple of hours, but can take also days or even weeks to come up with a reasonable number of simulations. But on the other hand, we can use machine learning algorithms or deep learning algorithms, if you will, not only for the sake of upscaling the representation of those reactive dissolution processes, but also to speed up the simulations, as well as accomplishing this under different conditions, depending on the conditions of the subsurface which is being under analysis. So basically, to accomplish these reactive dissolution with machine learning, we have two basic approaches for that. So the first one is what we call data-driven machine learning, which is typically performed by means of convolutional neural networks. And some examples of approaches which we have ResNet, UNet, general artificial network, adversarial networks, Bayesian networks, and so on and so forth. And normally they are fast, provide fast and accurate predictions, but on the other hand, they might be prone to overfitting, which require a large amount of data to accurately represent the phenomena that's occurring inside a subsurface. On the other hand, we have what we call physics-driven, which is done by physics-informed neural networks, which is basically done by coupling artificial neural networks with partial differential equations, which constrain the outputs of these physics-based models. So these partial differential equations, they essentially govern the phenomena that are being studied or that occurred inside the overall dissolution process. But the problem with them is that they typically have a slower turning time than the convolutional neural networks, which yield quite similar effort as those from numerical solvers. So that, let's go to the problem statement and the problem that we are trying to solve with our current project and how we tackle this. So first of all, we have a subsurface in which we want to analyze how the dissolution occurs over a specific amount of time. So given these initial properties here, the conditions of the reservoir, the subsurface at particular time steps, so we have several collection of input features. We have the concentration of the acid that is going to be injected into the subsurface. An epsilon, which tells pretty much the overall porosity of the subsurface, as well as the UX, which is the flow in the horizontal direction, and UI, which stands for the flow in the vertical direction. So we have these states for a particular number of subsequent time steps. So these will be fed as an input to the machine learning model, which in turn will try to predict the states for, again, a specific amount of time steps as well. So they have the same process, the same properties that are being fed as input, they are going to be predicted as output, but for future time steps. And this we use to grasp how the dissolution is occurring over a required number of time steps, a specific horizon. But typically the approaches for forecasting, when we think about predicting through a specific amount of time steps, we can think about some possibilities for that, for forecasting. So the first one is by what we call direct or independent strategy, on which that for each time step to be predicted with the same input data, we train separate machine learning models. So they're responsible for predicting the properties at time step one for time step 2, and so on and so forth. And naturally, this is a more expensive approach, as it requires to train one model at a time for each of the time steps. Another strategy is what we call recursive multi-step strategy. So we take a collection of input time steps to predict initially one time step ahead. So we use the same model to predict, to make multiple predictions, but at each step, we take the prediction from the previous step and we incorporate that into the input states, the input time steps to predict the next time step. So again, we use the same, so we need one model for that. We train only one model to predict only one time step given a specific number of time steps. But the problem with this strategy is the errors from previous predictions, they tend to accumulate as you predict for longer horizons. And another strategy for this is what we call multiple input, multiple output strategy, which takes, again, a sequence of input states, input time steps, and predict a fixed amount of time steps in the future. So typically, we can combine different strategies to get the best of each one. So this is why we came up with this strategy here. which is what we're proposing for tackling the reactive dissolution with machine learning. So we are basically combining the recursive multi-step approach with the multiple input and multiple output approach. So here's an example of how this works. So as an example, we're taking 5 time steps as input. We want to predict 5 time steps in the future. So we have, from the original data set, we have an initial, what we call perfect input, which is the states that actually happen in a data set, in a subsurface. So we have the original states for that. And we're trying to predict at first the next 5 time steps using what we call a Bayes network. And not only do this, but also it is known that if you train multiple levels of corrections for a machine learning model, so in other words, we have one machine learning model trained for a specific task, and we can train a second machine learning model to correct the mistakes from the first one, or at least mitigate mistakes as much as possible from the first network. And you can stack those corrections, can stack lots and lots of corrections, but there's a point until there's no further improvement. So you can set n to lower numbers, such as 3, 4, 5, depending on the problem is being solved. But basically, what we're trying to do is when we get the results from the first prediction for the Bayes network, so this is fed as input to the what we call level 1 network, which will provide a first level of correction over the subsequent 5 time steps. And again, this will be fed to a second level network, which try to perform another correction. And this is done so on and so forth until we reach the final level of correction and we have the final prediction of the next 5 time steps. So after doing this, you can, in order to grasp the dynamics of the reactive dissolution, you can predict as many time steps as you want in the future. So this is why we take, in the subsequent steps, we take the predictions at the sequence of networks here to feed again the Bayes network, which will predict, in this case, time steps 11 to 15, which in turn will be passed for the level 1. We provide a first correction for level 2, and so on and so forth until, so the process is done until you predict a certain amount of time steps at total. But talking about the machine learning algorithms, so we have come with 3 different neural networks that try to accomplish this task. So the first one is what we call encoder-decoder convolutional long short-term memory networks. So basically what it does is it takes a series of input states. So we have time step from time step n to time step n plus 9 here as an example. So it takes 10 time steps as inputs. So it performs a series of convolutions, just like done in the regular convolutional neural networks, until it reaches a latent representation, which will be decoded in the subsequent stages to predict, in this case, 10 time steps in the future. So it not only accounts for spatial features, but also for temporal dependencies between subsequent time steps as well. And the second approach is what we call the U-shaped Fourier neural operator, which is actually an evolution of the Fourier neural operator. So basically what it does is they switch from the domain of working with regular grid space, so basically images. So it switches from this particular domain to the frequency domain. So this approach was typically used for predicting gas saturation and pressure changes in subsurfaces. And the authors claim that changing to frequency domain, they can speed up the training and coming up with more accurate results, at least for the problems that they were trying to solve. But typically, it doesn't necessarily can adapt to every sort of problem, as we're going to see for the results for this particular work. And for the last approach that we try to do is what we call temporal rotation unit, which pretty much does similar to convolutional STMs in the sense of taking into account spatial and temporal features from the input data. So at the first stage, we have a spatial decoder, which will downsample the original inputs into more compact representations. And once we achieve this compact representation, it goes through a temporal rotation unit models, which will account for the not only the inter-frame difference, so the difference between consecutive time steps, but also the intra-frame difference as expressed in the loss function here. And after it does this, we decompress this the resulting tensor from the temporal potential unit model again to the spatial decoder to predict a certain amount of time steps in the future. Okay, so for our current training evaluation settings, we currently have a data set which consists of 32 simulation samples. So each of them has a shape of 100, representing the number of time steps. We have 4 input properties, which I described earlier, which are the concentration, the porosity, epsilon, the flow in the horizontal and vertical directions. And all of these maps have a size of 256 by 256. And for training each of the machine learning models, we separated 24 samples for training and other different samples for validation and test. And the data sets, they comprise the same dissolution regime for all samples. So have the Beckett-Lambert kinetic number equal to 1. The training algorithms, they're the ones I just mentioned. And regarding the correction, the stacking of machine learning models, we test up to level 3 correction. So we have the base model plus 3 levels of correction. And also input steps equal the output steps, which is 5. So we take 5 steps input, predict 5 in the future. And this is a recursive process. So we take this 5 from the output, feedback as the input for take the next 5, so on and so forth, until we reach these 100 time steps. And for assessing the quality of the predictions, we use the Pearson correlation coefficient, which is calculated for each of the predicted properties and for each time step. So the resulting maps compared to the ground truth according to this metric, and to see for each time step how the predicted property is similar to the ground truth for each case, each model from the training and the validation set as well. So for the results on predicting each of the 4 properties, so we have an average of the predictions from the training set and the 24 samples of the training set. And we can see here that both the UFNO and the temporal potential units yielded very good performances here. So we naturally have a degradation of performance because it's a recursive multi-step prediction. So it has this error accumulation problem. So we can notice as well that the UFNO and the TAU are more robust to this error accumulation. So the performance does not degrade that much for each of the cases, at least with the training set. But on the other hand, looking at the results of the validation on examples that were never seen before, we can notice that the UFNO in particular had a decrease in the general performance. It suggests that it's highly prone to overfitting, which doesn't happen with the convex TN and the temporal potential unit, which yielded the best results, as you can notice from the solid curve. So the average of all samples, all 8 samples from the validation set for each of those predicted properties, so C, epsilon, Ux, and Y. So the curves stayed above all the other ones, especially when considering the different levels of correction. So it's not very clear for TAU, for instance, but we can notice for the convex TM that for level 0, we have this performance. But as we stack levels of corrections for the convex TM, we can see the results increasing. But there's a point in which this stacking doesn't improve anymore. So we can notice that for level 3, we have a performance which is below level 2. So suggests that we can stop right there. For each network has a different situation when it comes to stacking multiple levels of correction. So we don't have enough time to go deep into all predictors of all properties, but let's show a couple of cases for one of the validation samples here. So for prediction of C, first we take a time step in the middle of the dissolution process. So remember we have a total of 100 time steps. So this is the results for time step 30. So we have here the predictions. Each row corresponds to a different level of correction. Level 0, remember, is the base level. And each column, we have the results for each of the machine learning algorithms, as well as the differences to the ground truth map for each case. And we can notice for prediction of the concentration, at this particular time step, we don't see that much of a difference between all the approaches. But we move to the very ending of the dissolution process. So we have, for the time step 100, we can notice, for instance, the convex TM at level 0. We have lots of noisy data, which has nothing to do with the ground truth. But if we stack multiple convex TMs, so we perform multiple levels of correction, we can notice that when we reach the time step 100, the resulting maps are much more similar to the ground truth in this case. Still, when comparing to the other approaches, the UFNO and the TAU, we can notice that even the level 3 of coverage TM is not better than level 0 of TAU, for instance, by looking solely at the correlation value. I don't know if it's possible to see here, but the correlation is, for this time step, is greater for level 0 of TAU than level 3 of convex TM, which, again, looking at the plot, that was a performance that was assessed already for the TAU. On average, it was better than both UFNO and convex TM networks. And here we have the predictions for the epsilon, which again states the overall porosity of the subsurface. And time step 30, we don't see, again, much difference between the approaches. But when we look at the time step 100, on which the dissolution is in a very advanced stage here, we can see this, for the ground truth map, you can see the channeling. So the acid is traversing this region of the subsurface here. But look at the predictions, we can notice again that for the TAU is slightly superior to the other approaches, particularly when looking at the correlation values. And with respect to the stacking of machine learning models, for this particular property, we don't see that much of improvement as well, except for the convex TM, which it started at 0.97 and ended at 0.99. But for both UFNO and the TAU, didn't have that much improvement. But we're just taking one validation sample from the 8 samples that we have. So we need to conduct a more substantial analysis over all properties and all models to see if this stacking actually works for all these machine learning models. So to conclude this presentation, so we can notice that we can actually use data-driven deep learning methods for predicting the dynamics of reactive dissolution on subsurface over a period of time. And the error accumulation from the recursive multi-step strategies, they can actually be mitigated when you consider spatial and temporal features, rather than traditional convolutional neural networks that use only spatial features. And finally, we can notice that the higher correlation values, they make it possible to replace the traditional solvers with machine learning solutions, not only because of the high correlations, but also it's capable of, you can train on a particular resolution. So we have trained for 256 by 256, but you can also apply to modeling to a different scale. So you can upscale this even more. So basically you can use these pre-trained, these trained machine learning models to solve the problem of upscaling, as I mentioned earlier. Okay, so that's it for today. So thank you very much again. And I'm waiting for some questions.
Thank you, Marcos. Thank you very much. Yeah, feel free to post your question again. So we will start with some from the studio then. So could you elaborate a bit more, Marcos, for the people in the audience on how training multiple level of correction mitigates error accumulation?
So I can repeat the question again?
Yeah, so could you elaborate a bit more on how training multiple level of correction in your recursive neural network help mitigating the error accumulation?
Well, as I mentioned, it typically works for easier problems, but with a much more complex problem than that. But here we can notice that for the convolutional LSTM, we have this evolution of the results over time. But the point is to actually provide with a higher performance on higher levels of correction is because we are feeding the results of the first output into the next one. So essentially, depending on the results of the prediction of the first five time steps, we can come up with future predictions which are can be better or worse. But if we manage to improve the first 5 on subsequent levels, then it is expected that the subsequent steps will be also will have minimal amounts of error as well.
Right. And so, and how do you explain then the difference between the different machine learning on this error accumulation? Like, how do you explain it? Do you have any insight for this?
Sorry, I'll just take a look at the comments here. Lost again.
Yep, no worries. So my question was, you said that there are difference in error accumulation between the different machine learning, especially on this slide. So can you provide some insight on why this happened?
Yeah, basically, what I said about the prediction of the first 5 time steps is when you stack the corrections for the subsequent stages. The idea is the next level minimizes produces a smaller error than the previous one, but essentially the original approach for that is quite different because when we talk about the level 0 prediction, we usually take the difference from the what was predicted at first to the ground truth, and then this residual is taken into account for the subsequent level, which then in turn try to make this correction for the second level, and the residual for that is taken for the next level. So the idea is to produce even smaller residuals at each level. So at each level, if you feed these residuals into the next level, so you can yield even smaller errors at subsequent levels. But there's a point again at which it doesn't work anymore, which varies from model to model.
Okay, so we'll take a question from the audience, and there is a need of clarification on what you refer as high correlation, and do you see opportunity to transfer such advantage into other contexts?
Well, by higher correlation, I mean basically high similarity to the ground truth. So let's go back to the this slide here. So due to this correlation method that we used, we have this degree of similarity between the predicted and the ground truth. You can use other metrics as well, such as the mean squared error or structured similarity error, which is basically used for images, and R-squared score, which is very popular metric as well. So by meaning high correlation, basically you can imagine as a high similarity. And to transfer to other context, well, I would say that because we're training on a particular subsurface which has particular conditions, particular geological formation, and but if you think about upscaling, because we're training on a particular resolution, that's then possible. So the model is totally adaptable to higher scales if you want to make use of this into a different context.
Yeah, thank you. I have actually a follow-up question on what you just mentioned. How do you expect your model to generalize to different geometries, different dissolution regimes? Do you need to train it back again?
Well, for now, we are using the data with the same dissolution regime. And usually it expects a common resolution, but that's pretty much the because the models when you perform the downscaling over the layers, the only thing you need to worry about is to feed with a resolution in which you can downscale properly and then perform upscaling again. So we usually take this as a power of 2 or something, and you control the number of internal downsampling layers. And so it's not that we can work with any sort of resolution. So let's say you have a resolution with the prime numbers, which you can divide at all, but it depends basically on the inner structure of the architecture, the neural network architecture. But after you train that, if the resolution you're trying to feed later, even though it's different from what was used in the training, if somehow it's compatible with the inner structure of the machine learning model, then yes, it can be adaptable to a different context.
Sounds good. Sounds promising for the future then. So, Hamid, do you have any question to Marcus?
I don't think so, being involved in the work, so I wouldn't be asking questions. So,
fair enough.
All right, so we don't have any more questions from the audience, so I think we can close the session. Thanks again to both our speakers today for sharing their research with us. Thank you for the audience for still engaging in this webinar series. Thank you, Ahmed, for co-sharing. And please don't forget to subscribe to our YouTube channel to never miss a future webinar. And yeah, thank you, everyone. Bye.